as 1,000, right? If we wanted to get super picky about that, okay? We could then write that out as 1 kilometer. We could make the abbreviation all the way down to km, and we could end up with that kind of expression. That expression in and of itself isn't useful, but what I can do is rearrange that expression to solve for 1. And that becomes powerful, because when I go through to solve an equation, ultimately all I'm doing is multiplying or dividing by 1. And that's how you solve virtually all of your algebra expressions, is multiplying by 1. It's just a question of which one are you multiplying by. Right? So we've got the kilometers written out here. Typically people memorize this as 1 kilometer equals 1,000 meters. Okay? So I want to switch this around just a little bit, and before we advance to the next slide, what if I said centimeters and meters? Has anybody memorized relationship between centimeters and meters?
Yeah.
What do we got?
100.
100 what?
Centimeters into 1 meter.
Okay. Let's take a look at the formatting of that for a second and compare that to the formatting up here. Anybody notice something different about it? Okay. The 1 is first. Okay, so let's flip that. I can fix that real quickly. 1,000. Yeah? So let's fix that one issue. So now identical, right? No differences?
Units are different.
So the units are different, well, but they are different numerical things, so it does make sense for the units to be different. Okay. Maybe it would help if instead of writing it out as the longhand numbers, we wrote it out as scientific notation. Maybe that would help draw attention to what I'm trying to point out here. That's 10 to the third meters is 1 kilometer. This would be 10 to the second centimeters is 1 meter. Does that help draw your attention to anything interesting about those or different about those relationships? Yeah? What's the difference?
Well, the exponent, obviously, but would that be the difference between?
That's the difference in those units. So, and this is one of the problems that we're going to fight with conversions. Okay? Is you're going to lock onto numbers. 2. 2. What the hell are you talking about, Mike, right? Okay, 2 apples. Okay, 2 arrows. Do those have different meanings? If I say 2 arrows are coming at you versus 2 apples, you might change your response a little bit differently. Okay? So the numerical value is actually useless. Okay? And what you need to focus on is not the numerical value, but what is tied to that numerical value. So with that lens, what's our difference? Someone pointed out 1, so let's point out 1. Let's highlight the 1 in green. What is the 1 tied to in the red? Kilometers. The complex unit, right? Because there's 2 letters that represent it. Move to the other one. Where's the 1 tied to? The core unit. We've changed where our numbers are aligned. Well, why on earth would we do that? Okay. What did centi mean? Centi means 100. Let's go up here and take a look at centi. That means 100. 10 to the minus 2 means 100. That means hundredth, not 100. But isn't that 100? What? Okay. If we follow what I'm telling you to do when you memorize these, is that you should memorize that centi is 10 to the minus 2. Okay? 10 to the minus 2 equals centi. What if I now want to reference this as centimeters?
And you change the
Centimeters, where should I put the other m? Right on the other side. What number goes in front of centimeters? 1. 1 centimeter is 10 to the minus 2 meters. Is that what you guys told me earlier?
Yes.
That says 1 centimeter is 10 to the minus 2 meters.
Flipped. It's a reciprocal.
Okay, it's a flip. It's a reciprocal. The numbers have switched around. Why would we do that?
Converting in different directions.
Why? Why bother to do that inversion?
To get smaller or bigger.
Is it getting smaller or bigger?
Smaller. It's smaller.
I heard no. No was the right answer to that. It's not getting smaller or bigger. It's the exact same thing.
No, but like
Okay. Why, instead of writing 10 to the minus 2 meters is 1 centimeter, that's what it means. That's literally the definition of centi. Why on earth did you instead memorize 10 to the second centimeters is 1 meter? Hold up. When I asked that relation for the numbers between centimeters and meters, did you tell me 10 to the second? No. You actually told me 100. Why are we making these decisions to switch? Why did you memorize in blue and yet the definition is what is in black? So those of you that memorized what was in blue, how did you memorize that? You're just like, ta-da, I knew the answer. The prefix, what's the prefix mean?
100.
Look at the definition. The prefix does not mean 100. That is false as a statement. How did you decide that 100 centimeters equals 1 meter? Where did that come from? Exponential notation is 10 to the minus 2. So no, where did 100 centimeters equals 1 meter come from?
We were told.
You were told that. Why were you told that now? You were told that by somebody older than you. Okay? They were older than you, and they were probably told that by somebody older than them, and older than them, and older than them. Because it went so far back that what did they not have the ability to process well? Because remember, when we went through to format this, we said that was the same thing as 10 to the second. Did they say 10 to the second? No. What could they not process? Exponential values. The exponential value was too hard to process. I don't want to think about it. So what am I going to do? Instead of using the exponential value of 10 to the second, I'm just going to multiply it out and write 100. Okay? Let's push it further, because it's not 10 to the second. What is it? 10 to the negative second. So not only was that really old person unable to deal with powers of 10, they were also numerically challenged with negative powers of 10. So when people go, oh, scientific notation, I totally get it. No, you freaking don't. Okay? This is why you didn't memorize powers of 10 in scientific notation in the past. Okay? Our human brain has a very hard time dealing with that. So what did we do? Those old people went through and said, well, that expression is too hard for me to manipulate, so I'm going to start to write this out. So 10 to the negative 2. What does that negative sign mean? Do it in the denominator. Actually, no. The negative sign does not mean do it in the denominator, because if I say 1 over 10 to the negative 2, it's already in the denominator. What does the negative sign mean?
moving the value to the right of the decimal. Left. The decimal's moving left. The value's moving right.
Okay? So we heard move the decimal which direction? It gets smaller. What is 1 over 10 to the minus 2? It is 100. Did the number get smaller? No. So this, it's just moving the decimal. No, it's not. You're doing it wrong. Okay? You've memorized a process, an algorithm that no one has pushed you on. Guess what I'm going to do? I'm going to push you on it, and I'm going to break you because you're going to end up doing something stupid. Okay? What is the meaning of a negative sign? What is my speed in this direction? 2 miles per hour. What is my speed in that direction? Negative 2 miles an hour. Why? I was going in the opposite direction. What does the minus sign mean? Do it opposite. In that 1 over 10 to the minus 2, where's my calculation currently? Numerator or the denominator? It's in the denominator. So if I take that red number, what does that minus sign mean? Do the calculation in the opposite location. What is the opposite location of a denominator? That's exactly what it means. You can throw in, it's just the inverse. You're using different mathematical terms to now explain something that all it is just run the calculation in the opposite location. Okay? Why would we bother to do something like that? Well, it's just shifting the decimal point. No, we just proved that multiple times. You're wrong. It's not just shifting the decimal point. We don't do well with powers of 10. We don't do well with negatives. Okay? So someone went through and said, well, if I multiply all of that out, 10 to the negative 2, I can get that to become 1 over 100 meters. Well, that's better. There's no powers of 10, and there's no negatives, right? Except now what do I have? I have a fraction, which also sucks. So what do?
Simplify it.
How do I simplify it? I could change it to 0.01, and now I have a decimal. Okay? As we just saw with decimal shifting points, we're also not good at that. Can I change this so I don't have to worry about a fraction anymore? I what?
Multiply across.
Sort of. I multiply both sides by 100.
Which is not the same as cross multiply. It's not.
Because I'm doing the same thing to both sides, I'm allowed to do this. This is effectively multiplying by 1. And now what happens? I end up with 100 centimeters equals 1 meter. You're like, why? Why would I bother do all that? Were you good with powers of 10? No. Were you good with negative signs? No. So what do? You convert it into a system that doesn't require you to deal with that. Okay? Do we have devices that are good at powers of 10? Do we have devices that are good at negative powers of 10? Yeah. Do we need to spend some time memorizing a potentially flawed mechanism? Because notice, centimeters versus 1 meter was not the same when we did kilometers and meter. We changed where our numbers were located. Okay? If we just memorize what they are as a power of 10, I now know exactly where to place every single time my power of 10. My power of 10 will always go with the core unit. I don't have to memorize, well, how do I convert that into something that's not a power of 10? Because a freaking calculator does it for me. So those older people that taught you to memorize this 100 centimeters is 1 meter, it's just easy, you should do that. Okay? It's just easy because that conversion was too hard for them. It was too hard for them because they didn't have a calculator. Okay? And when you're 7, that process takes a little bit of effort. Did you have a calculator when you were 7? No. Okay. What do you have now? A calculator. You got the internet memes all over the place. You're a 7th grade math teacher. You'll never have a calculator on you everywhere. It's called my cell phone. You're wrong. Which means don't use an archaic memorization system that will ultimately fail because you have to memorize where all of those placements of numbers go. If you memorize just the definition, the numerical placement is consistent and constant every single time. Okay? The relationship on how we convert between the black and the blue is dealing with what that minus sign means and how we would run the calculations behind it. Okay? So the reason I point this out is that this can simplify if you do what I'm telling you to memorize. If you decide not to, that is quite all right. You will encounter questions that will push your limits, and your success rate drops from being 90 plus success rate to maybe 70 plus % success rate. Well, that's not that big of a deal. 90 plus is an A, 70 plus is a C. Okay? And that assumes everything else you're doing is correct. Okay? I want you to be 90% right, not 70% right. Okay? And a lot of the processing that I'm giving you may seem like, oh, it's a bunch of extra work. That extra work is to ensure that you get the answer right 90+% of the time. The shortcuts that you will often encounter, particularly when it comes to conversions and Lewis structures and nomenclature and chemistry in general, work 70% of the time. Okay? And they are oftentimes easy to confuse and screw up later on because you've lost the process behind it. So what you need to be thinking about when we move through is, what is that process? What is the process I'm trying to get you to figure out? Okay? Particularly when it comes to conversions, I really don't care that you can convert inches to feet. Okay? What I do care is that you have a process that works so that when I change it to skittle farts and snorlaxies, you can do that conversion like it's second nature. Okay? Bless you. Okay, so there's that negative thing, so we'll ignore that and kind of move on. Okay, and continuing to move on because we already talked about all that. So converting is a process. Okay, your textbook calls this the unit factor method. I've heard it referenced as the factor label, dimensional analysis. Dimensional analysis is what I go through and call it. Okay, your textbook sets it up this way. When I first saw it, I was like, this is crap. You don't need to do that. This organization behind it is actually very, very good. Every time you see a conversion question or a calculation that you need to do, you need to start with what you want for an answer. You then need to place what you're given. And then you need to decide how you can convert across. Okay? That is your basic process behind it. We're going to change those terms around here in just a second because I stumbled across a repeatable phrase that I find irritating, but I said it and everybody seems to like it. Okay? This is a process. Not I multiply by 12. Not I shift the decimal point 2 places. Okay? Those cases are algorithmic and they may work for 1 or 2 questions. They won't work for all of them. Guess when this process works? All of the time. Okay? A lot of people struggle with physics. Guess what? Physics is just one giant conversion. Everything done in physics can boil down to this exact process. Okay? Which I found exceedingly frustrating when I discovered that. Just for the record. Greg.
So, as like Mike said, that's a process, and the first thing, the thing he's showing you is really a rhetorical intention thing. When I presented the project to you guys just a few minutes ago, one of the first questions was asked was, like, wait, what am I supposed to be doing? You guys were trying to identify the goal of the project, right? that's the same thing. When you are looking at unit conversions, you're really asking a rhetorical question with science. You're saying, what am I really trying to accomplish through this string of conversions? Depending on my goal will change the steps I take along the way. Does that make sense? So that's a rhetorical part of science.
I can't put that one in there yet. What this is effectively asking is every time you see a question is you need to ask yourself, what do I want? That needs to get identified right away. Then you've got to decide, what do you have? Identify that right away. Okay? The next part, what do you want over what do you have? Why? If the have is in the denominator, what does it do with the have over here in the numerator? It cancels out. And what are we left with? What do we want? Okay? There it is. Okay? So you have to ask yourself every single time, what do you want? What do you have? Okay? There's an extra little question that should come with this. Does this exist? Did I spell that right? Is that better? Okay. You have to decide, is that relationship, does that actually exist? Because there are cases where it won't exist, which means what do you have to do? This could be a different one. So the question is now changed for you. You would then have to go through and say, different one.
Does this exist like?
Does that conversion factor exist? Okay. So for instance, if I want to go into inches and I'm given, sure, let's do this. Milliliters and I want inches cubed. Okay. So what I would do, okay, what do I have? I have milliliters, inches cubed. Does that conversion factor exist? Okay. Could you make a conversion factor that does that? Yes. Making does not mean it exists. You have to create a conversion factor, which means that does not exist. So you're going to have to convert that into something else. We could decide that I'm going to convert those milliliters into centimeters cubed, because that conversion factor exists. Okay, now I have a new question, and I'm trying to convert centimeters cubed into inches cubed. Does that conversion factor exist?
Yes.
What is it?
Centimeters to inches.
Is it centimeters to inches?
Well, inches.
A cubic inch is the exact same thing as 1 inch.
12 times 3, yeah. You have to cube it.
You would have to cube it, which means you're inventing a new conversion factor. So what would that mean? It doesn't exist. What do you need to do? You would need to repeat that conversion 3 times to get there. You could also cube it. We'll address that when we get there. Okay? So when we go through to do a solve, it's this same basic process. What do I want? What do I have? Now I start putting a relationship together to try and establish that. There will be times, okay, where you don't know if it exists. That sucks. Now you start guessing at what you could possibly convert it to and hope that it somehow comes out. That comes with practice. Okay? For this first unit, the what do you want and what do you have, those conversion factors will be given to you. Okay? They will be conversion factors that you probably already know. Inches, feet. What's that conversion? 12 inches, 1 foot. Okay? Believe it or not, I think I give that one to you. Seconds, minutes. 60 seconds is 1 minute. Okay? Inches, centimeters.
2.3 or 4.
Okay? It's It's one of those numbers. So we had one person that was like, I think I know that. Unfortunately, it was wrong. The rest of you are like, I didn't know that. Guess what? I give it to you on the exam. All of those conversion factors that I don't want you to memorize, but I do want you to use, will be found on the very first page of the exam. Take a look at exam 1. Very bottom of it, guess what you see? A bunch of conversion factors. They've been there since day 1. You're now going to have to start manipulating and using them. Okay? So, guess what happens in Unit 3? I pretty much take those away. Okay? And it's not that I take those conversion factors away, it's that we bring in other ones that you have to know relationships for. Okay? That information is encoded. You just have to be able to decode it. Where is it encoded? Periodic table. Where else is it encoded? You're not using the textbook on the exam, so no. There's a conversion factor embedded in that formula. What's that conversion factor? There are 2 hydrogens and 1 oxygen in water. So I have a conversion factor. 2 hydrogen atoms equals 1 oxygen atom. When is that true? When I'm looking at water. Because if I change the formula, it's no longer true. So we're going to have conditional conversion factors. Those conditional conversion factors will depend on what you're looking at, or the conditions, which is why we don't give you a list of them, because we'd also have to give you all of the conditions. Okay? So think of every possible chemical formula you can think of, probably multiply by that like 6,000 or 7,000. Okay? And now list that all in a first page of your exam. Okay? Not going to work so hot. Okay? Do we have another conversion factor that you already know how to interpret? Probably. Good idea. Let's pick another simple one. Is there a conversion factor embedded in there? Yeah? What is it? Okay. O2 to O. Does O exist in this? Okay. For O to exist, it would have to be where? All by myself. Does O exist in this? Does O exist in this? Do I see an O all by itself? Where? Left side of the equation. There is a single O all by itself there. No. Does O exist? Nope. Okay. What's your conversion factor? Bam. The subscript we've already looked at. We just saw that when we looked at H2O. So yes, the subscript provides a conversion factor. But I already saw that. Maybe what we should be doing is looking on top of that. The what? What do those coefficients mean? I need 2 hydrogens and 1 oxygen. When do I need that? To make water. So I have a conversion factor that relates hydrogen gas to oxygen gas, only under the conditions that I'm making water. So if that's the reaction I'm looking at, I now have a way to relate those 2 substances. Whoa! That's the meaning of all those numbers. They weren't just random things we threw in there. Those atoms, or those, numbers, allowed us to count how many of those pieces were involved in those reactions. We have to be able to use that to create a conversion. So remember we said multiply by 1,000 all the chemicals that you could possibly think of? Now think about all of the chemical reactions you can possibly think of. Okay? Remember, if you had 7,000 chemicals, each of those 7,000 chemicals could react with any number of the other ones. There's a few. The front of the exam now becomes really, really challenging. Okay? So we need to be able to interpret what a formula means, what an equation means, and to be able to pull those conversion factors out. That's what Unit 3 is driving at. Okay? So you have to know how to find those. That becomes more challenging, particularly because on top of that, what are you then going to have to do? Convert it into a different substance. So if you don't know how to convert, you're dead in the water. If you don't know the meaning of your formulas, you're dead in the water. If you don't know how to balance equations, you're dead in the water. Okay? Unit 3 requires all of Unit 2. Okay? We're struggling with Unit 2 a little bit, because guess what Unit 2 is based off of? Unit 1. All of the content builds, and it only gets more and more complex. This is why you have to constantly be going backwards and forwards to build that content knowledge forwards. Okay? It's challenging, but it allows you now to apply it to a much broader situation than if we just said, here's a formula to solve. Okay? Because I'm pretty sure you can all multiply by 12. Okay? I think you can find those buttons in a calculator. I'm okay being an ass. Which, for the record, was recorded, if you're curious, 31:35. Why do conversions matter? So somebody came up with this little cartoon. Okay, water, 1 mile, 1 kilometer. Americans, we're going to go the 1 mile to water. Okay, that in and of itself is funny and hilarious. Like, oh my God, people are just making fun of Americans being idiots because they don't understand the difference between that. Followed by the tweet, but the Americans are right. Because 1 mile is less than a kilometer. 1 mile is 1.61 kilometers. You have to be able to apply the numbers in the correct locations. It's not just, that means that is 1.6 and that is 1. Okay? You have to understand how those numbers get aligned with each other. Okay? How do you align those numbers with each other? The conversion process. Okay? So whenever we go, I just need to multiply by 12, divide by 3. I just need to multiply by 1.6. You do to the right freaking place. Okay? So it's not just throw a number at it. You have to know where to throw the number. The location of where comes from that conversion process and the proper placement of units. Should we look at that conversion? Sure. Okay? I need to make sure that I can make a fair comparison between these as my dead and dying American crawls up to these signs. Okay, 1 mile, 1 kilometer. They're not in the same unit system. I need to get them into the same unit system. Which one do I want to convert?
I convert miles.
Okay, you're going to convert miles. So that means your target is kilometers. I want mile in the denominator in that calculation because it's what I have and I want to get rid of it. And what do I want? What's the conversion? 1.6 goes in front of the kilometers, which means if we now sub that into our diagram, this becomes the Americans going the wrong way. That's not an attempt to be political, but it's pretty accurate. Okay? So we have to be careful with how we approach these things and be logical and systematic. Yes?
Okay, so but what if we I don't know if this makes sense, but what if we don't know it's 1.6?
Let's say you don't know the conversion. So let's switch this up. Which way is right now? What was that? Yeah, what is an ST? Because you knew what a PK was? Okay. What do we do if we don't know? Well, in this situation, yeah, I pull out the quarter, I flip it, and I just pick a direction and I go. Okay. If you don't know, you can't solve. Okay. That's a whole nother issue because you literally don't know that step to be able to establish it. Okay. In this case, all of the information was factual. It was all correct. Okay. We had to have that information. We had to know that conversion. Okay. Which does bring in kind of another statement. Who said that 1 mile was 1.6 kilometers? And don't tell me the person in that picture. General consensus. As a scientific community, we got together and said, this is the standard. Okay? That is a completely arbitrary human invention that has no basis whatsoever in reality other than we've created it. Okay? PK and STs could be the perfectly valid measurement system somewhere else. Okay? So we have to know that sociocultural norm. If we don't, we can't bridge that gap. Okay? And that becomes challenging because that now brings in access. Okay? If people don't know the standard, everything they do, they've lost access to that material. That's a really big issue. Okay? And what science is trying to do is standardize it so that everybody has that access, okay, or can get access to it. It's not a perfect system, but that's the hope.
So pretty much when you give us these questions, do you want us to solve it in the fractional notation form?
You need to show some form of work behind it. In that work, the crux of that is not that you can punch numbers into a calculator. The crux of that is why did you place numbers where you did to do that calculation, which is ultimately the units. So every time we go through and solve, what drives our placement of numbers is the units. So I don't care necessarily where you place the numbers, I care where you place the units. In that process, should you be using dimensional analysis? Yes. Why? Because it works. How often? Every time. Not some of the time. This isn't a 90% success rate. This is a 99.99999% success rate. Okay? Dimensional analysis is phenomenally repeatable. The only times it fails is when you misplace things. Okay? Entering things into a calculator fails a lot more frequently because all you're doing is punching buttons. Okay? And I hate to draw this analogy, but if all you're doing is punching buttons in a calculator, I can pay a monkey to do that better. Okay? I don't want you to have the job of a monkey. Okay? I want you to have a much better job than that. I want you to be able to design a process to pay a monkey to do it. Okay? That's what I want you to do. Okay? That said, you can be happy with the job of the monkey and just punching buttons. That's okay too. Okay? But most of our high-paying jobs aren't trainable to monkeys or to computers. Okay? You're adding a level of cognition beyond what we can put into a computer and beyond what we can put into a monkey, at least currently. I mean, monkeys are getting smarter, right? Okay? Make sense? Just challenging, I know. Okay, so enough about monkeys. Let's look at classifying chemical reactions. We've got all our chemical reactions, so let's take a look at a few of these. We're going to take a look at the single replacement reaction. Single replacement reactions are much more difficult than our combination and decomposition because you are required to predict the products. Okay? Still, haven't freaking fixed this slide. So let's delete that. what would you predict the product to be? Or products? So you're given that equation. What should your products be? Give me a second. Where is zinc on the periodic table? Right there. I heard someone say the word I was looking for. Left of the staircase, which makes it a metal. Where's PB? Left of the staircase. Metal. Sulfur. Oxygen. Nonmetals. If we look at our basic format, we're taking the two things that are the same color and they exchange. That same color is representing what? Could push to cations. Believe it or not, we can't expand it outwards than that. And that's why we're pushing a little bit more different here. We're exchanging the two things that are the same. In this case, I have a metal in one place, and then I have a metal and a nonmetal in the other. When I go through to run the reaction, what am I going to do? Swap the metals. Okay. For that swap, what were you suggesting, Aiden?
Lead, zinc sulfate.
Say that again?
Lead, PB, zinc sulfate.
Okay. I don't know that made it into the recording, so we'll say it again. The suggestion for the answer was lead plus zinc sulfate. Did I write that? No, why not? I didn't put lead in front. Does 2 plus 1, what does it equal? 3. How about 1 plus 2? Does the order matter? No. When we're doing the addition, the order does not matter, so we don't have stress on that. With the zinc sulfate, could I have written it SO4ZN? Sociocultural norms. Our norm in this case is that we need to include the cation or the positively charged species, also known as the metal, first. So the order in the formula does matter. The order in the equation does not. Okay, there were a couple hands that floated out there. Maybe you, Hayden? I definitely saw David. What'd you get?
I was just saying, no, because it had a positive charge on the
Yeah, okay. Have we predicted a product? That was a yes or no. So you're shouting out like all this other stuff. It's yes or no. Okay, we heard some yeses and some nos. We have predicted chemical formulas. We've not predicted a product officially yet because we haven't finished it. With our chemical equations, we should be specifying the phase of our substances. So we should also be layering phase information behind this. With the single replacement, you'll notice in the generic form, I did not specify the phases. Okay? Why? Because I hate writing phases. It's also one of the reasons why I don't teach 151. Okay? I just don't like phases. Okay? That said, you're still required to show them here. Okay? The phase does a full swap too. Okay? Meaning, if zinc pairs up with sulfate, the phase becomes aqueous. If the lead goes off by itself, its phase becomes solid. Okay? So cool, we've now predicted. Okay, we predicted what would happen in this single replacement reaction. Is that a hand or just, no? Okay. So let's add another layer because there's another layer behind this. If I win the lottery, I'm going to buy a Tesla. And I'll buy one of the really big, larger ones because I got kids and I want to put the kids in the thing and I want it to go fast. Does that mean I'm going to go buy a Tesla? But that's my plan. If. What is a chemical equation? If. Okay? If this chemical equation happens, this would be the result. Does it happen? For a single replacement reaction, you are responsible for being able to do that. Ouch. However, you are not responsible for being able to do that with the information that is currently on the board. Okay? We're missing something. Okay? For you to be able to decide, does this reaction actually happen, you need more information. That more information is an activity series. Okay? So now with that more information, does this chemical reaction happen? Come on, I gave you more information. Shouldn't you figure it out? Some people are like, yeah, I got it. And the rest of you are like, what the hell? Yeah, accept that. That's fine. You should be like, hell no, I don't understand that. Tell me. We need to have that conversation. If you don't tell me, I can't help. Right? What does the activity series measure? Likelihood of a reaction. So we're going to switch this up. Let's look at it as, see if I can do this nicely. Let's do this. Let's try this. Social activity. Okay? So the lower on this, if you were socially active, okay, the lower on this scale, you would be what? More or less active? Less active. Okay? Admittedly, I did just erase the sign that said decreasing. I apologize. Okay? The bottom is less active. Okay? So they're introverts. As being less active, they would be introverts. Okay? Let's go. Let's go up to the top of this. I just want to walk away from all of what's going on over there. If we were at the top of this list, we would be more active. And instead of an introvert, we would be extroverts. If you didn't hear it, don't worry. Just close your eyes. Extroverts. And please don't repeat. Okay? Extroverts, introverts. If you are an extrovert, what are you more likely to be found with? People. So lithium would be expected, if I look for it in the world, where would I find it? With other elements. Gold, on the other hand, all by itself. And we already sang that, so I'm not saying that again. Okay? How do we use this information up here? Do I care about lithium or gold? No, I care about zinc and lead. So I need to find zinc and lead on my little chart here. There's my zinc. There's my lead. What does that mean? Okay, so we could go medium in between, but that doesn't do anything with the question that I was being asked. Does the reaction happen? I'll elaborate. Zinc is more active than lead. That means when I look at this plan for what could possibly happen, I want to find zinc partnered with something. Because zinc is more active than lead. Where is zinc partnered with something? Right there, right? Okay. So we looked at the extrovert. Some of us are introverts. So let's look at the introvert aspect too. Lead is the introvert, which means where should it show up? On its own. Where does lead show up by itself? On the right. Should this reaction happen, if I mix zinc solid with lead sulfate, do either of them want to be in those states? No. Zinc would rather be partnered with something else. So what is the zinc going to do? It's going to combine with something else. But to do that, it has to kick lead out. So lead will then chill by itself. Look the side of the reaction that I underlined. Which side of the reaction was that? I underlined the reactant side. I underlined the product side. Did this reaction happen? Yes. Here's a bunch of examples. Start trying. So let's go ahead and move forward. We're going to skip the second one. The second one should be straightforward. You should be able to do that one. There's nothing particularly tricky or standoffish about that one. The third one down does have a little bit of trick going on with it. So if we go through, I've underlined the metals and the nonmetals. So we'll exchange. Aluminum goes by itself. Silver should now be paired with the chloride. This is typically what I will see students write. Yep.
No. Because AG has 1 and CL has...
Okay.
minus.
In your prediction, so Christian is right on top of this. In your prediction of your products, you have to ensure that you're drawing a proper product. Okay? So what do we mean by that? Why is that 3 being written there? So those people that wrote that 3, why did you write that 3 next to the chlorine? What do you mean there's 3 chlorines? Well, couldn't I write a 4 there? Then there would be 4 chlorines.
We only started with 3.
You're writing a 3 there, not because that's a 3, but because that's a 3. Right? The logic that you are using is that because there's a 3 there, there must be a 3 on the other side. Okay? I'm going to make... Stop. Sorry. I'm going to change that 3 to a green 3 now. Why is that 3 there? Not Christian, because I know he knows the answer. Sorry. Why do I have the green 3?
Because the charge on aluminum is 3.
Aluminum is a +3. Chloride's a -1. I need 3 chlorides to balance out the charge of the aluminum. That 3 is there to balance aluminum. If we now go to the other side of the equation, where we said we had 3, now that red 3 with the black circle around it, why should that 3 be there? Okay. If your argument is because the green 3 was 3, well, the green 3 was there because it was bonded to aluminum. Is the red chlorine bonded to aluminum anymore? No. So that argument is invalid. Okay?
Can't gold have 3 charges on it as well?
Someone want to answer that?
Have 1, 2, or 3, I know that.
That's silver.
Silver. It's okay. Gold is the next one. AU.
Oh.
Okay. It's okay. Yes.
I'm kind of confused on why it's not AgCl then Al. Like, why is it Al then AgCl?
So remember the order here. 2 + 1 versus 1 + 2. The order of the addition does not matter. I can switch up that order as much as I want.
Okay.
Doesn't
Okay.
aluminum have more activity than silver?
We haven't even gotten there yet.
Can you write the answer to the second one just to make sure?
I'll do that right at the end of class. Yes.
How do we know the charge of AG?
So, how many chlorides should be partnered with the silver?
It's only going to be
Okay. Silver, you are required, to Christian's question, silver, you are required to know the charge on is a +1. Chloride is a -1.
Well, that's why you're not taking it.
Okay. Silver is a +1. So how many chlorides do I need to balance the silver? 1. So that formula is AgCl. Okay. That is now a proper formula. Okay. We're going to ignore solubility. For those of you that want to deal with solubility, don't. Okay. And we'll just go through and say our phases transfer the same, solid, and then aqueous. That's a Q. Okay. And now a couple people are jumping up, but then the chloride isn't balanced. Did we ask you to balance the equation? Yeah. Not yet. Okay. So now that you've addressed the weakness, fix it. How do we balance it? Feel free to tell me your steps anytime. Start with AG. How many do we have? 1 and 1. Move to aluminum. How many do we have? 1 and 1. Chlorine. 3 and 1. Way to switch up the pattern on me. I appreciate that. All right, how do we fix it? I need a 3 here. So that then becomes 3. Now what happens? Now we go back and check all of our work. And that checking of the work, what do we notice? 1 and 3. That needs to become a 3. Put a 3 there. Aluminums. 1 and 1. Chlorines. 3 and 3. Some of the coefficients. 8. I asked that pretty fast.
Oh, okay.
Sorry, that was me intentionally trying to be a jerk. Remember there's implied 1s there? So you get a total of 8 for your sum of the coefficients. You've now shown a balanced equation. You've predicted what would happen. Should it happen? No, why not? Okay, we did all of that work, and really the conclusion of all of that work is that what we drew should never happen. Okay? That's a valid conclusion. Okay? That is useful information. Finding out what doesn't work is just as useful, if sometimes more so, than finding out that it does work. When students do well in classes, they don't know what they don't know. As soon as we push you and cause you to realize that you don't know things, now you have an incentive to start learning to figure out what's going on.
But could
Right?
they figure that out without writing all that stuff?
Is there ways that you can shortcut this? Yes, just like there's ways to shortcut conversions. What becomes the success rate? Okay? It is all about the success rate. Okay? If you are successful in shortcutting it, all that you're going to do is piss me off. But that's it. Okay? If you are not successful in your shortcut, you're still going to piss me off. Okay? And I'll then be like, neener, 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 you should have done what I told you to do. Okay? And I might even bring some lemon and salt. Okay? So, with that, how do we decide? We need to identify silver and aluminum on the chart. There's silver. Where did aluminum go? There it is. It's not below it. That works. Aluminum is higher in activity, which means aluminum wants to be with something. Where is aluminum with something? On the left-hand side of the equation. Silver is lower in activity, which means it wants to be by itself. Where is that? On the left. If I mix those two reactants together, what happens? Nothing. They're not going to produce products because silver is already where it wants to be. Aluminum is already where it wants to be. There's no reason to do an exchange. Okay? Yes?
So let's say instead of silver it was like zinc, then it would react?
Where's zinc? Nope. Zinc is still lower.
Oh, so that's
So instead of silver, if we went to magnesium, sodium, calcium, potassium, or lithium, then it would react. Okay? We will do a lab on this that tweaks it a little bit. This is how we're going to talk about it in lecture. This is how I'll test on it in lecture too. Okay? So, anybody notice anything interesting about the bottom of the activity series? Why are they precious? Actually aren't that rare. Like, when you compare rarities, they aren't that bad. They're shiny. All of the metals are shiny. Shinier. Lithium's pretty dang shiny. And lithium is even cooler. Like, I add lithium to water, and what happens? Pff, I get a fireball. Like, that's cool. Why don't I base all of my jewelry off of lithium? I don't want to take a shower. Because I step into the shower and my finger explodes off when the water touches the ring. Okay? That becomes problematic. Why do we have silver, platinum, and gold all at the bottom of our activity series? They don't react. Why do we value them as currency? Because they don't react. If we picked lithium, let's imagine Fort Knox and we decided lithium was our currency. Okay? What do we got to do? We attack Fort Knox with water balloons. Okay? They have sprinklers freaking inside the building to put out fires. All we got to do is come in with a match. Poof! All of it dissolves, goes down the drain. There goes the entire country's currency system. Okay? We picked precious metals based off of their chemistry. Okay? That's kind of neat. They don't react. Okay? Last one I wanted to, actually no, it's a lie. So I wanted to look at that silver and aluminum one. I will come back and show that one, I promise, but I'm going to continue on and we'll come back to it at the very, very end. Okay? So, I do not expect you to memorize the activity series, particularly because it should show all the metals. Does this all the metals? No. Okay, so I will give you an activity series. It won't have just the metals you need. It'll have some other ones in there that just there to mess with your head. That's it.
Thank you.
You're welcome. Okay? But I will give you some kind of condensed format of it. Okay? Active metals, the textbook talks about these. I really just want to throw it out there just so you're aware of it. Some of those metals on that activity series are so active that they will react with water. Okay? Because they're so active, we call them active metals. Okay? That's it. Okay? So they will go through and do a reaction with water. You don't need to stress about the details behind that. Just be aware that it does happen. Okay? Which is really going to set us up for our oxidation and reduction chapter, which is a bit of a doozy. Okay? If you went through and watched the video, you probably saw this concept of dealing with charge and oxidation. If we take a look at this reaction, because that's going to get dizzying for a second, so let's pause that. If we look at the course of this reaction, what is the charge on calcium in the reactant? Where do you see charge? The upper right-hand corner. Is there anything specified for the charge on that calcium? No. So what is its charge? It is 0. Let's go over to calcium on the product side. Where's the charge specified? Top right-hand corner of the compound. And it is a 0 charge for the compound. I don't want to ask for the compound. I want to know calcium.
That would be a positive 2.
It's going to be a positive 2. Hydroxide, we know, is a -1 from nomenclature, because you were told to memorize it. There's 2 of them, which means the calcium must have a +2. What is charge? Baby, don't hurt me. Sorry. The balance of, say it again? Electrons and protons. So to go from a 0 to a +2, what happened? That balance changed, right? Did we change the protons? No. How do we know that? Because it's still calcium. Okay? We still see the symbol Ca, which means the electrons changed. Okay? How did the electrons change? To go from a 0 to a +2, what did I do? But I became positive? How? If I lose something, how do I become positive?
So you got 1 positive.
We have to remember the charge on an electron being negative. A loss of a negative is a positive. So this was loss of electrons. Does anybody see electrons in the equation? No. So those electrons are being lost. Well, what are they being lost to? They aren't shown in the equation, which means something has to be picking them up. If we go through and look at the rest of the atoms through this, we will find that our hydrogen started as a +1 and it became 0. To go from a +1 to a 0, what did we have to do? We had to gain an electron because it was negative, right? That negative taking me to a positive to the 0. Okay? So the 2 electrons that calcium lost, hydrogen gained. But it only needs to gain 1. Where'd the other electron go? 2 hydrogens were converted across. The coefficients from our equation are allowing us to see that. Right? What we're now referencing is not charge, but oxidation state. Right? The way it gets presented to you is as charge first. Let's just say it gets presented as charge first, right? And then we shift to oxidation state. Oxidation state applies to the balance of protons and electrons for an atom. Charge is the balance of protons and electrons for anything. So we could look at the charge for a calcium ion. The charge would be +2. Its oxidation state happens to be +2. The charge and the oxidation state in that case are the same thing. That is not always true, but that's where the underlying confusion comes in. They're always referencing the balance of protons and electrons. If you're only looking at an atom, we can refer to that as the oxidation state. But the oxidation state is never specified, it's calculated. So when I say calcium +2, what is that +2? It's its charge. How do I determine the oxidation state? Well, it's the number of the element. How many elements showed up in that? 1. Times the oxidation state. Well, I don't know what it is. I got to solve for it. That must equal the charge. What's the charge? +2, which means oxidation state is +2. Right? So the oxidation state is only for an individual atom. Charge applies to a larger unit. That unit could be a single atom. It is typically a larger molecule. Okay? And it is typically, when we talk about charge, for an ionic compound, not for covalence. Right? So when we go through and look at oxidation and reduction, it's just a question of how we apply that. So we need to be able to assign oxidation states to every single element. Right? Once we've assigned oxidation states to every single element, we can then go through and define, did it gain electrons or did it lose electrons? Okay? That's relatively straightforward, right? Gain of electrons, that's an awful lot of letters. What do we do as lazy people? We invent a word to represent gain of electrons. And we call it GER. GER is not a word, it's an acronym. Gain of electrons, GER, must be an R word. Reduction, what happened to the number? To go from a +5 to a 0, what do I do with it? I reduced it. Gain of electrons is reduction. Loss of electrons is oxidation. And we just came through with the fancy term of Leo says GER is our acronym. If you memorize oil rig, boo.